Alright, we're going to continue with our second lesson today on graphing. So in our first lesson we looked at using x and y intercepts to help us draw a graph. Today we're going to figure out asymptote lines. So you should have learned horizontal and vertical already in Math 30-1, so the only new one today will be doing oblique or diagonal asymptotes. So we'll go through them in the order that I'd recommend that you do these questions. So we'll start with vertical. So remember, with vertical asymptotes, these occur whenever we have non-permissible values. So when we're looking at a fraction, something, if I gave you something like x plus 1 divided by x minus 3, the problem is our denominator, if x was equal to 3, that would give us our dividing by 0. So the easiest way to do it is just determine what your non-permissibles are, and that should be your vertical asymptotes. The one scenario that we got to be careful of is, remember, if I had two different factors on the top and we still had our x minus 3 on the bottom, that x minus 3 is not a vertical asymptote. That would be our point of discontinuity. So we just got to be careful of which type's which. So I would still start with your vertical, factor everything completely, and then you should be able to easily tell which. So let's go through a couple examples. So this first one, here's our function. So first thing I would do is factor the denominator. So if we factor the bottom, we'll get x plus 4 and x plus 2. So you can see neither of those will cancel out with the top. So both of those will be asymptote lines. So all we're doing mathematically is we're just figuring out where are those things going to equal 0. So for the first one, it'll be at -4, and for our second one, it would be at -2, just by solving those mini equations. So the simplest way to write this is just say your vertical asymptotes are going to equal x of -4 and -2. Okay, so I usually just use VA to indicate your vertical asymptote. And that'll be it for the first one. Okay. Second, we have another one. So this one again looks fairly similar, but this time if we factor the bottom, we can see that we run into a problem. We have x minus 3 and we have x plus 2 as the other factor. So in this case, the x minus 3 would cancel. That one's going to be our point of discontinuity. So we'll know we'll have a point of discontinuity when x is 3. And remember, once we cancel it, this equation would simplify to just 1 over x plus 2. So if we plug that 3 into here, that would give us 1/5 as our point of discontinuity. So that point will not be a vertical asymptote, but the other factor, the x plus 2, would be. So in this case, we'd say we have a vertical asymptote at x equals -2. And then remember, we can do exactly what we were doing in the previous lesson. With all of this stuff, it should just help us sketch our graph better. So our vertical asymptote at -2, we could still draw that. We have still our x, if we plug in a 0 for x, our x-intercept would be -3 over 6. Our y-intercept would be -3 over 6. So which would give us -1/2 or +1/2. So we could have that on our graph as to be a little bit more accurate. We could do our x-intercept, which will be based on our top factor, right? So that would be our 3, but that was our pod. So in this case, we don't have any x-intercepts, and we already got our pod at 3 1/5. So just from that, we would have a little bit more information to sketch our graph. So just by eyeballing that, I would pretty safe to say, oh, our pod should have been an open dot. So we should have a graph that looks something like that. So closed dot at the x-intercept, open dot at the point of discontinuity, and we probably have a matching curve going something like that on the other side. So once we work on our other asymptotes and our other details, we'll be able to finish off the graph, but all of the same stuff that we did previously would still apply. Okay, here's another one. So in this case, the top doesn't factor, so we don't have to worry about that. And the bottom does, so we would get +4 and -2. So in this case, both of those would be our vertical asymptotes. We'd have them at -4 and +2. So remember to do the opposite sign because we're making what value would make those things equal to 0. Okay, here's two more, and these ones are both a little bit tougher because we can't factor the bottom easily. So if you ever run into a situation where you can't factor it just by normal sum and products or whatever, probably your best bet is use the quadratic formula. So I'll just rewrite the formula here. So if we have our equation, we could always plug it into quadratic formula to determine those values. So in this case, if we plug in our A will be 1, B will be -5, C will be 7. So if we plug it in the first case, you'd have -5 plus or minus square root of 25 minus 4 times 1 times 7 is 28 divided by 2. And we can see that would simplify to -√3, or root of -3, which doesn't exist, right? You can't do a negative square root. So that means this one would have no vertical asymptotes. If it doesn't have a solution, there's no vertical asymptotes. Okay. If we try the same thing with this second one, it's almost the same equation, but the signs are switched. So we'd end up getting +5. Oops, I messed that up on the first one. It doesn't affect our answer, but our first one should have been +5. Negative of -5 would have been +5. And now for this one, we should get -5. And then the inside would be 25 minus 4 times 1 times -7 will give us +28 this time, all over 2. So if we simplify it here, we do get solutions this time because it's root 53. And we could leave it like that, or it might be easier to change them to decimals. So if we go -5 plus root 53 divided by 2, that'll give us about -1.14 approximately. And if we go -5 minus root 53 divided by 2, that'll give us -6.14. Actually, that should be positive for the first one, right? -5 plus 7 would be roughly 2, yeah. So that should be plus 1.14, and then our other one would be at -6.14 as an approximate decimal. Okay, so those would be the worst case scenario where you have to do some harder factoring to get those solutions. But it's still just what are the non-permissibles of the bottom values. Okay, so let's move on to horizontal asymptotes. So horizontal asymptotes, if you remember in Math 30, we sort of did a couple of different ways of treating it. Sometimes we looked at them as a transformation equation, but I think most people found it easier just to do the shortcut. So our shortcut was, if I gave you an equation like 4x minus 3 over -2x plus 1, our shortcut was we just divided these front coefficients, and then we said our horizontal asymptote was at y equals -2. 4 divided by -2 gave us -2. The reason why that works, we're actually doing a limit. So I'll show you on the next page how that actually should work. So that's one option of solving it, and it's probably the easiest and quickest. The second option is we could treat it as an inverse. If we have a graph where we do the inverse, remember if we flip our x and y axis around, we know how to calculate vertical asymptotes. So if we did the inverse of that same equation, that would then change it to a horizontal asymptote. So that's another option of doing it, and I'll show you one of those too, but most people generally don't like to do it that way because it's a little bit more work. So for this one, let's look at it from how the shortcut, we can just use the shortcut and see that our horizontal asymptote would be 1 divided by 1. So we would just get it at y equals 1. So that's pretty simple. But let's quickly remind us how this works. So if you remember back to our first unit, our horizontal asymptotes actually showed up when we did our infinite limits. So we would do the infinite limit of this equation, or it could be negative infinity, it doesn't really matter, they both work the same. So if you remember back when we did limits, the way to do infinite limit questions is we would actually change the question by dividing by the highest coefficient. So in this case, x is the highest coefficient, so we would divide every term by x, and then we would simplify that. So that's what it would turn into. Then when we simplify it, we would get 1 plus 1 over x divided by 1 minus 2 over x. And then we had a limit law that we used where if limit as something approached infinity of 1 over x, we said that was eventually going to be 0. So that means both of these would turn into zeros, so we just get the 1 over 1. So that's where this shortcut coefficient idea comes from. It's actually using our infinite limits. But we can just use the shortcut for sure. It'll always. So the other method is kind of an interesting one. If we took our equation, the y equals x plus 1, and we do the inverse, so we can trade the x and y values and resolve it that way, or we can just leave them as x and y, and that's totally fine, but let's solve it for x. So if you take this equation and you solve for x, that'll also work. So you can see on the side here, we basically just bring the x minus 2 up, so I'll just kind of rewrite it along with it here. So you'd have y times x minus 2 equals x plus 1. Then if we FOIL that out, so you'd have x times y minus 2 times y. And then what we're going to do, just like when we do dy dx's, we're going to bring the x to the one side, bring the 2y to the other side. So we would get xy minus x equals 1 plus 2y. Or 2y plus 1, doesn't really matter how you write it. And then we would common factor out an x. And then divide out those brackets. So all we did is we just took this equation and rewrote it as x equals instead of y equals. So that would be the inverse. So that means we would still do the denominator. So in this case, y equals 1 would be the non-permissible value, but since it's the y, that will make our horizontal asymptote. So you can see it works the same as dividing the coefficients, just it's a little bit more work. So most people don't do it this way, but it is kind of a clever way of solving the equation. So a couple quick examples. So for this one, if we divide by our highest power, 2x divided by x would give us 2 over 1. So that means our horizontal asymptote should be located at y equals 2. So that's all you have to do for horizontal. Quite easy. Here's another one. Just be careful the way they're written. Sometimes people get mixed up with the order, but we're still dividing our highest coefficients. So in this case, it'd be 2 over negative 4. So our horizontal asymptotes should be at negative 1/2. Okay. One thing we got to be careful of too is sometimes the powers aren't always going to match. So remember, if I gave you something like 2x minus 3, but now we're going to divide it by x squared plus 5, we can still use this shortcut. Just remember though, it has to be the highest power. So if we have x squared on the bottom, that means we'd have a 0x squared on the top. So now we would have 0 divided by 1, which would still be 0. So in this case, our horizontal asymptote would be the y-axis. Or sorry, the x-axis. Okay? Or the one other scenario, what would happen if the bottom was smaller than the top? So if I gave you something like x plus 5 on the bottom, but now we had 3x squared minus 7 on the top, we would still divide our highest power. So in this case, you'd have 3 on the top divided by 0. Well, we can't divide by 0, right? This doesn't exist. So what that means is there's going to be no horizontal asymptote. Okay, so that's our one scenario. And that actually leads us to what we're doing next. So if we don't have a horizontal asymptote, what that usually means is we're going to have an oblique asymptote instead. So that's what we'll learn next, and that's basically our only new stuff for this unit, or for this topic. So our oblique asymptotes are going to be a diagonal or a slanted line instead of a horizontal or a vertical line. And this only happens when the top of the fraction is bigger than the bottom. And for this course, we're only going to worry about it when the top is one bigger power. So if I gave you something like 4x squared on the top, if it had just a single x on the bottom, that would give us an oblique asymptote line. And it doesn't matter what the rest of the equation looks like. We only worry about those highest powers. So if the highest power is one bigger on the top, that'll always give us an oblique situation. And the method we're going to use to solve for that oblique equation will be long division. Because it's going to be a slanted line, our oblique asymptote equation, instead of it just being y equals or x equals like it was for horizontal and vertical, it's going to look like a linear line. So we're going to get equations in the form of y equals mx plus b. So we'll do a little bit of practice with long division so you remember how to do that, and there's one little other important part for it, and that's pretty much it. So here's our first example. So we look at it, we would have our vertical asymptote at x equals 2, so that's good. Our horizontal asymptote in this case would be 3x squared divided by 0x squared, which means there's none or doesn't exist. Okay, so that means we likely have an oblique asymptote. So we know our equation should be y equals mx plus b, so the question is, how do we figure it out? So if we do our long division, so let's write it as x, oh, my pen's not working, let's try this. There we go. So we're going to take our top 3x squared, so let's put that on the inside. Let me erase that out of the way. We'll put that on the inside of the long division, so we'll have x minus 2 divides into 3x squared plus 4x plus 5. So we don't have to do the entire long division, we just need to get the linear equation part out of it. So let's do this entire question, then I'll explain that more in detail. So for this one, if we do our long division, remember the first step is we want to ask ourselves, how many times does x divide into 3x squared? Or if you look at the original question, really all we got to do is actually divide those first two terms. 3x squared divided by x will give us 3x. So that's our first part of our oblique asymptote. We're going to get y equals 3x. So our next step is we need to FOIL that out. So 3x times x would be 3x squared. 3x times negative 2 would be negative 6x. Our next step is we need to subtract these from what's above. And we got to subtract the whole thing. So the way I would write it is go 3x minus all of it like I did in brackets, and then let's change our signs to the opposite. So we'd have 3x squared minus 3x squared would be 0. 4 plus 6x would be 10x. And we can bring down the 5 if we're going to do the entire question. And now we start all over again. So instead of going 3x squared divided by x like we did, in this case we're going to go 10x divided by x minus 2. So we kind of do the same thing, just divide those front terms. So 10x divided by x would be plus 10. And we FOIL that out again, that would give us 10x minus 20. And again, if we subtract all of this stuff, change our signs, we would get 0x, and then 25 would be our remainder. So in Math 30, when we did long division, we would say this equation, so if we kind of went right from our original equation, we would say that after we divide it out would equal 3x plus 10, and then we'd have our remainder of 25 divided by x minus 2. The nice part about this stuff when we're doing oblique asymptotes is we only actually need to worry about the answer, the 3x plus 10. The remainder doesn't matter because all that's going to do is it goes back to sort of a limit idea again. We're going to be calculating what happens for an asymptote line when x gets really, really big. So we're going to be doing the limit of this remainder, which would end up eventually being 0. As that x value gets bigger and bigger, we would just get a 0 for an answer, so that's not going to affect our equation. If we were to graph this out, let me just sketch a graph here quick. So if we were to graph this equation, we had our vertical asymptote at 2. Our horizontal was 3x plus 10, so that'll be a pretty steep line way up here somewhere. So those would be our two asymptote lines. So now when we draw our graph, it would be somewhere in between those two, kind of like that. So the remainder, that remainder value, what that's going to affect is that spacing when the x values get closer to the intersection point. When they get further and further away, that's when we're going to be getting closer and closer to positive and negative infinity, so it'll eventually be 0. So at x of 1, this value is actually doing quite a bit, right? 25 divided by 1 minus 2 is a pretty serious thing. So that would affect our coordinate. But when x is 100 or 1000 or 1 million, this eventually becomes 0. So it doesn't affect our asymptote line. We only worry about the extreme locations. So because of that, the long division actually is even easier. We don't need to complete the whole thing. We just need to worry about the first 2 parts. So this next one, let's do the same. Okay, so let's write it as x minus 1 dividing into 3x squared plus 4x plus 2. So again, our first step, we just got to worry about 3x squared divided by x. So that'll give us 3x as our answer. FOIL that out. So 3x times x would be 3x squared. 3x times negative 1 would be negative 3x. And then we want to subtract all of this. So let's change our signs. So that would give us 0, and then we'd have 7x left over. Okay, we don't need to bring down the 2 because that's not going to affect our question anyway. We just need to get the remainder. So our next step would be take this leftover part and divide it by x again. So our leftover answer should be plus 7. And we don't even need to finish the question. We're done. That's our answer right there. So our oblique asymptote for this question should be y equals 3x plus 7. Okay, so you're basically just dividing your front coefficients, 3x squared divided by x, which gave us 3x, and then we divide our remainder after our first step, divided by x once again, and that'll give you your last part of the equation, and you can stop there. Okay, here's another one. Let's find the oblique asymptote for this one. So if we do the same thing, let's go x plus 1 divided into x squared minus 4x minus 5. And we follow our same process. X squared divided by x would be x. FOIL that out, gives us x squared plus x. Subtract these. So that would switch our signs. So we'd end up with 0, and then we'd have negative 5x. Negative 5x divided by x would give us minus 5. And we're done. So that would be our oblique asymptote line. But if we actually graph this one, this is a weird thing what happens with this one. If you actually put this original equation on your calculator, it'll look something like this. So that is the equation of our oblique asymptote line, but that's what our graph is going to look like too. So in this case, our graph and the asymptote are the exact same thing. So what's weird, and is where you got to be really careful, is do not jump right to oblique asymptotes, because we might have done all this work for nothing, and that's what actually happened in this case. If we would have calculated from our original equation, if we would have calculated our vertical asymptotes first, so if we would have factored our top equation, we would have got x minus 5 and x plus 1. So you can see the x plus 1 would have cancelled, so that gives us, we have no vertical asymptotes, because there's nothing left on the bottom, but we would have got a point of discontinuity at negative 1. And it ends up being at negative 1, negative 6. So what's weird is, I drew my graph wrong. The graph wouldn't have looked like this. It would be down at negative 5. I went the wrong direction. So our graph should have been down here somewhere. Okay, so what we're seeing is, if we go back to the original equation, we would have no vertical asymptotes. Our horizontal would be 1x squared divided by 0x squared, so there's none of those. And because our equation simplified to just y equals x minus 5, that means we have no oblique asymptotes either. So this is no asymptotes at all. All we would have had was x-intercepts of 5. So when x is 5, we would have got y of 0, so that would have been that location. Our Our y-intercept would have been the other way around. When x is 0, we would have got -5. And we figured out our pod was at -1, -6, so that would have been a bullet hole right there. And that's it. That's our graph. So it is worth it to make sure you go through the steps. Do vertical first, then do horizontal, then do oblique last. That'll save you any chances. Okay, my last example I have here is just higher powers. It has cubes and fourths, but it doesn't really matter. And you can plug in zeros if you want. Some people like to put a 0 in for all the missing terms, but I'm not going to. The only thing I'm going to do is I'm going to rewrite the top from highest to lowest. Okay, and like I said, you could put in a 0x cubed and a 0 at the end if you want, but you don't actually need to, because we're still just going to divide these out. So our first step is to go -x to the fourth divided by x cubed. So that gives us -1x. Foil those out, so we'd have -x to the fourth, and then -1 times -x would be plus x. So I'm just going to write it over there because there is no x squared once we FOIL it out. And that's the only thing you got to be careful of. So now when we subtract these and change our signs, you can see the x to the fourths cancel, the x's cancel, the only thing we had left over is x squared. And we can do the exact same thing again. We would go x squared divided by x cubed, but it's already smaller. So that means the x squared is our remainder. So there is nothing left to divide out. So we don't even need to worry about it. We're basically done. The top value is our oblique asymptote. So our equation in this case would just be y equals -x. We wouldn't have any other plus or minus number. Okay, so that's basically it. I would say it's a good habit to get into. So if you were going to do this question, I would graph the original equation. I would also graph y equals -x on your calculator. That would give you that asymptote line. Our vertical asymptote in this case would be a 1, I think, so our graph would look something like that. We have no horizontals, and then I would just plug the equation on your calculator. So in this case, we would end up with, I'm guessing without doing too much work, we're going to probably get two curves that look something like that. But just by looking at it on your screen, you would actually see if your asymptote lines are right. Our vertical asymptote of x equals 1 and our oblique asymptote of y equals -x. If you did those right, they should look appropriate on your calculator screen. Alright, our last case thing that we need to talk about is what happens if we have functions that aren't polynomial rational type graphs. So the only other kind of function, so we looked at polynomials, which we just did. We've done square root graphs, which don't have asymptote lines, so we don't have to worry about those in this situation. Trig doesn't have asymptotes, so the only other scenario we have is log and exponents. So if you get a log or an exponent equation, what I would do is, let's just worry about the exponent one first. So what I would do in this case is think of it as a transformation. That's probably the simplest bet. So for this first one, if we were to remember this from a transformation point of view, our graph should, a regular exponent graph, look something like that, where it crosses at 1, and then we typically have our horizontal asymptote at y equals 0. So our regular equation, and it doesn't matter what it is, any y equals something to the x, like 2 to the x, or 5 to the x, or e to the x, they would all just have a horizontal asymptote at 0. So all I would do is look at this from that perspective. So in this case, if we did a vertical stretch of 3, that's not going to affect the asymptote line. We do a horizontal stretch of a half, that's not going to affect the asymptote line. But the 5 down will, right? If we move this thing 5 down, our asymptote line will also be 5 down, and then our graph would be from there. So in terms of horizontal asymptotes for an exponential graph, I would just look at your translation. So if there's an up or down translation, that would be the location of the horizontal asymptote. So in this case, our answer should just be y equals -5. Okay, and it works the same with logarithms. Let me move over to the logarithm side. So in this case, if we do the same thing, if we look at it from a graphing perspective, Remember, a log graph follows the y-axis and then curves up. And again, it doesn't really matter what we could have an equation that looks something like y equals log base 3. It would look like this, or it could be a natural log. They're all kind of roughly the same graph. So in this case, our vertical asymptote is located at x equals 0. So again, from a transformation perspective, we would just have to figure out, is that thing moving left or right? So if we go back to our original equation, the only issue with this one is we'd want to factor this out. So we'd see that we'd have a 1/2 horizontal stretch, it would be reflected, and then we went 3 to the right. So in this case, our vertical asymptote should be located at x equals 3. With logarithms, and it kind of works with exponents too, if you can't remember the transformation logic, you can also think of a log can never be negative. We can never have a negative value. So our log would have to be bigger than 0. So that means algebraically, if you wanted to solve this, we just got to take whatever's after the logarithm part in brackets and figure out where is that going to equal 0. So if we mathematically solve this equation, bring the 6 to the other side, and divide by, oops, I screwed up my equation, it was 2x plus 6. So when we bring it to the other side, it'd be -6, so -6 divided by -2 would give us 3. So you can see that gives us the exact same answer. Our vertical asymptote would be at 3. So algebraically, you can do it that way, otherwise transformation makes perfect sense too for these. Let me just go back to the exponent one, because we could actually do it sort of the same sort of way. So if we were to look at this original equation, we could have rearranged it first to make it y minus 5 equals 3e to the 2x, and we could have even divided by 3, so let's do that. So you'd have y minus 5 divided by 3 equals e to the 2x. And then if we want, we could switch this to a logarithm. So basically just do the inverse. So now we'd have natural log of y minus 5 divided by 3 equals 2x. And then we could divide by 2, so we could even write it as 1/2 ln of, let's write it as 1/3. Is this going to work? Am I messing it up? I did mess it up. Bringing the 5 over right at the start would have been +5, sorry, not -5. So we'd add +5, then we would have divided by 3, and then we would have did the, change it to a log. So if we write it as 1/3 y, actually we can just leave it the way we had it, that probably works just fine. So we'd have 1/3, or y plus 5 divided by 3. So the 1/3 is just a decimal, right? That would just be our stretch, our horizontal stretch. That's not going to do anything, but let's just leave it the way we had it. So this will equal x. So we could do it similarly to what we just did. We can't have a negative log, so that means all we got to do is solve this fraction to make it equal to 0. So if we bring the 3 up, that's why the 3 didn't really matter. We still just get y plus 5 equal to 0. Bring the 5 to the other side, that would give us -5. So you can see it does give us the exact same answer. So you don't need to do this algebra for log or exponents. It's probably simpler just treat it as a transformation and figure out if they're moving left, right, or up or down. And that's totally good enough for these kinds of questions. So that's it for asymptotes. So horizontal, vertical, and oblique. Need to do all 3, and that'll help us draw these graphs a little bit more accurately.